Hello guys, welcome back again. My name is Amit and it's good time. So we are finally back again with part 3 of the arrays and mathematics in our DSA lecture series. So today we'll be covering some new topics in arrays and mathematics. So before we move on, I just wanted to share something. So it has been recently seen that a lot of people that come to the channel who see the videos, they either do not watch the videos till the end. So it's my humble request that you do watch the videos till the end because it takes a lot of effort and time from my side because I have to actually take out time from whatever I have to make these videos, and I try to put my utmost effort, in making these videos. So I would request that everyone watches the videos till the end, and anyone who is new to the channel, do subscribe. Your support is very much needed. Okay, and if and always do like the videos, comment. Okay, this actually motivates me to make such quality content more and more and to continue this DSA series. So I also need motivation, and I also need that urge to do to continue the thing, and that actually comes from your side. So as an audience, what you can do is that you can show your appreciation in the comment section, or by liking the video or by subscribing. So that was my message. And also, a lot of people who watch the video are not subscribing, so it's my humble request that you do subscribe and press the bell icon so that you never miss an update. And that was all. So now we'll move on to the topic. And today we'll be covering about segmented sieve, and let's dive into it. So let's start the topic for today's video. So today we'll be talking about segmented sieve. So before we move on to segmented sieve, I would just like anyone who's seeing this video for the first time. So I would like to recommend that you go and watch the previous video about sieve of Eratosthenes. So that is basically the prerequisite for this video. When you will know about the sieve, then only you can learn about segmented sieve. So the link will be in the top right corner. So you can go and check out that video first. After watching that video, you can come back. Okay, and nevertheless, so today we'll be covering about segmented sieve. So first of all, we have covered till now is about what is sieve. So sieve is basically a very efficient way. Sieve is an efficient way of calculating primes, right? Efficient way for calculating primes. Okay, very good. And what was the range in which this algorithm was working? So basically, let's say we want to find the number of all the prime numbers from 1 to n. We could employ this algorithm, right? And typically the value of n can go up to 10 to the power of 6. So up till this point, your algorithm will work fine and very efficiently. The time complexity of the c was what? N into log of n. And we actually have also given a formal proof that how does this come. You can go and check out that video. So that is very good. Okay, very well. That we have a very efficient algorithm that works fine. Okay, very good. What about big numbers? What about large numbers? Let's say I want to find the prime numbers from 10 to the power of 8 up to 10 to the power of 10. What about them? We can see that if we try to use the same sieve algorithm, the normal sieve algorithm that you have, then if we try to employ that thing on this range, we cannot do that, right? Because simply creating an array of size n when n is 10 to the power of 8 is not possible. Okay, it is not possible to assign the size of the array to 10 to the power of 8, right? And even if you are able to assign, let's say by some magic you're able to assign that amount of value, the runtime, if you see, it's already beyond 1 second, right? It's already beyond 1 second. Let's say 10 to the power of 10, you'll be beyond 1 second very easily, right? So this means that for bigger numbers, normal sieve is not going to work. Normal sieve is not going to work. But okay, very well. Then what do we do? How do we deal with bigger numbers? We have something known as the lifesaver, that is segmented sieve. Here comes our lifesaver, which is segmented sieve. Okay, but segmented sieve also has some has some limitations. Okay, it's not like that for any given range. For, let's say, if I want to calculate the number of primes from 10 to the power of 10 to, let's say, 10 to the power of 16, it's not possible. Okay, even segmented sieve comes with some kind of limitations. And what are those limitations? Okay, so before moving on, I just wanted like to point out that this topic is actually very helpful for anyone who is starting out in computer programming, and even who are grinding Leetcode specifically for hard questions and medium questions. It might be possible that in questions of number theory, you might face such kind of question where you would need to calculate prime numbers in between a range where the numbers are very big. Let's say you need to find the prime numbers in between such big range. Then segmented sieve comes in very handy. So that's why this algorithm is also very important. So that's why it's good to go through this algorithm. Okay, and for computer programming people, it's a boon. Okay, so nevertheless, not a problem. Everyone should know about this. So as I said, that segmented sieve also comes with some limitations. Okay, so segmented sieve is not very different from the normal sieve. We also mark the the values as prime or not. Let's say we had some value like 10 to the power of 8, and we had given some range like 10 to the power of 8 plus some n value. Okay, so what do? We also mark these elements as prime or not prime. Okay, the same what we do in normal C, we also do in segmented C, but this is actually something different. Okay, it's not exactly like the normal C that you see. It's a bit different. So what do we do? What do we do is, first of all, let's know about the constraints when this can work. Constraints, let me just pull it up. Constraints of segmented C. Segmented sieve is actually very is very powerful, as it helps us deal with bigger numbers, but it has a very basic limitation. Okay, the first thing is whatever the value of L and R that you have, it cannot go beyond 10 to the power of 12. Okay, this is the first condition, that your R cannot go, that ending range cannot go beyond 10 to the power of 12. Okay, that's the first thing, that whenever you see such big numbers, you can easily employ segmented sieve. If your value of R is bigger than 10 to the power of 12, or like 10 to the power of 16 or 10 to the power of 18, it might be possible that some else, some other logic is going to be used. Okay, some other technique is going to be used, but you cannot use segmented sieve in such for numbers bigger than 10 to the power of 12. That is the first thing, that your L and R can only go up to 10 to the power of 12. Okay, that is the first important thing. What's the second limitation? The second limitation is that the difference between these values, R minus L, should be less than or equal to the power of 6. And now you see what is the major limitation of this segmented sieve. You can deal with large numbers, but at the same time, the range of numbers that you're going to deal with is still going to be stuck within 10 to the power of 6. Okay, again, as I say, let's say you had like 10 to the power of 8, then you can only check up to 10 to the power of 8 plus 10 to the power of 6, not beyond that. Not beyond that. Okay, even when you are dealing with bigger numbers, the range difference should be always upper bounded by 10 to the power of 6. It should not go 10 to the power of 8 or 10 to the power of 9. Okay, the difference between R and L should always be less than equal to 10 to the power of 6, because that is actually maximum that you can use or you can define to an array size, right? 10 to the power of 6 से आप ऊपर नहीं जा सकते. This is the maximum size that you can make an array of, right? You can also go to 10 power of 7, but for just to be on the safe side, we are going to 10 power of 6. Okay, so these are the major two limitations of segmented C, that this is the first thing, that R cannot go beyond the power of 12, and the same time the difference between R minus L, that whatever range has been given to you that mark the primes in this range difference cannot go beyond 10 to the power of 6. Okay, this is not recommended, this is not suggested, because this will not work. Okay, so these two limitations are basic to the segmented sieve, and if your problem constraints are well within these limitations, these constraints, then you are good to go to use segmented sieve. Okay, so how does segmented sieve actually work? For this thing, we need to go a step behind, and let's talk about how do we actually calculate these things. Okay, let's say I want to calculate all the prime numbers from range 50 to 100. Okay, let's say I had 50 to 100. Okay, the first thing that comes to the mind is what are the prime, what are the divisors of a number? As we have discussed in previous videos, the divisors of a number can be generated within SQRT n number of iterations, correct? अगर आपको 50 कैसे आइट्रेशन जानने हैं, तो बेसिकली 7 7 is 49. So basically up till 7 you'll be able to cover up all the the factors of number 50. Okay, so basically from starting from 1, if you go to 7, you'll be able to cover up all the the divisors of number 50. So segmented sieve is somewhat starts in a similar way. What do we do is, first of all, we mark all the prime factors from 1 up to SQRT of R. Step 1 is what? Step 1 is generate, or let's say mark all prime factors, not prime factors, basically prime numbers from 1 up to SQRT of R. Why SQRT of R? We know that since L is less than R, therefore SQRT of L would be less than SQRT of R. Therefore we can surely say that the divisors of number L are always upper bounded by the divisors of number R, क्योंकि सिंपल सी बात है, L के divisors हमेशा R से छोटे ही निकलेंगे. Okay, so this means what we'll do, we'll first of all try to calculate all the prime numbers from 1. We'll try to generate or mark all the prime numbers from 1 up to sqrt of r. Remember this, not up to r but to sqrt of r. Why? As we know that r can go up to 10 to the power of 12. This means sqrt r can go up to 10 to the power of 6. This means that we can easily make an array of size 10 to the power of 6. So first, let's say we need to calculate the prime numbers in this range. So what we do, we calculate all the primes from 1 to sqrt of r. So let's do that. Okay, let's do that. So like we had what we had 1, okay, and 2 and 3 and 4. In this way, we have an array of sqrtr. So sqrt of r is what? Sqrt of r, we can see it is up till 10, right? So since it is 10, we can say our array will be of size what? Will be of size 10. So we can directly make an array of size 10. All right, 1 2 3 4 5 6 7 8 9, and this is 10. Okay, so let's number them up. So this is 1, this is 2, this is 3, this is 4 5 6 7 8 9 and 10. So let's mark the prime numbers. So we'll use the basic same sieve algorithm that we know about, the normal sieve जो पिछले हमने वीडियो में पढ़ा था. So we'll just use the same algorithm to mark the prime numbers from 1 up to sqrtr. So here r was 100, so sqrtr is what? 10, right? So let's mark the prime numbers. So first we'll cancel all the composite numbers. There's a composite number, there's a composite number, a composite number, a composite number, a composite number, and composite number. So we are left with what? We are left with 2, 3, 5, 7. So these are basically the prime numbers from 1 up to sqrtr, right? So after marking them, what we'll do, step 2 is extract them. Step 2, extract them and store them in an array. Extract them, store them. तो हम क्या करेंगे, बेसिकली जितने भी प्राइम फैक्टर्स हमने निकाल लिए हैं, ऑल द प्राइम, नॉट प्राइम फैक्टर्स, ऑल द प्राइम नंबर्स फ्रॉम 1 अप टू sqrtr, we'll just push them or store them in an array or a vector, whatever you want. Okay, whatever you want, you'll just store them. Okay, now what do we do is the interesting part. Now as we know that for 50, let's talk about 50, and let's talk about 100. Okay, so we basically know that when we're talking about 2, so basically we need to mark all the multiples of 2 in this range. We need to mark all the multiples of this number in this range. Okay, so first of all, what we do before going on marking the multiples, what do? We create a temporary array, or let's say a prime array, a new prime array. And what will be its size? Its size will be equal to r minus l plus 1. So this will be 100 minus 50 plus 1, a 51 sized array. Okay, so what we are basically going to do, we are going to transform this range. We are going to basically transform this range into indexes from 0 up to 50. That is what we are going to do. Just a lot of you might have heard about transformation. So we are doing nothing extraordinary here. We are just translating the range of 50 to 100 into 0 to 50. So हम क्या कर रहे हैं, हम just 50 to 100 वाले जो range है उसको 0 से लेकर 50 के बीच में represent कर रहे हैं. We have just changed the representation. हमने बस representation change किया है, so that we'll be able to store them in an array, or we'll be able to use an array for marking them as prime or not prime. Okay, so how do we do it? So as we said that now we would have created a 51 sized array. हमारे पास एक ऐसे start करके ऐसे बड़ा सा एक array होगा 51 size का. Okay, pardon my drawing. Okay, it's not very good, but bear with me. Okay, so ऐसे हमारे पास ऐसे करते करते एक बहुत लंबा सा array होगा 51 size का. Okay, यहाँ पर 50 इंडेक्स होगा, यहाँ पर 0 होगा. Okay, so now what do we do? हमारे पास हमारे सारे प्राइम्स हैं, right? We had all our prime numbers that we had extracted. They were 2, 3, 5, 7. Okay, now we will start iterating over that range. Okay, remember हमारी range जो है, जो उसका जो साइज है वो कहां तक जाता है, 10 की पावर 6 तक जाता है. इसका मतलब अभी भी हम वेल विद इन द कंस्ट्रेंट है. ओके, तो हम स्टार्ट करेंगे 50s और 100 के बीच में. ओके, सबसे पहले हमें लेट्स से हम 2 को लेते हैं. नाउ वेयर शुड वी स्टार्ट? हम क्या कर सकते हैं, या तो 4 को मार्क करें, 6 को मार्क करें, 8 को मार्क करें, पर ये सब तो एरे में है ही नहीं. दे आर नॉट इन द एरे, राइट? व्हाट वी हैव डन, वी हैव translated these things to an array, right? The 0th index basically represents number 50. It does not represent the number 2 or 4. Okay, so first what we can do is, where should we start? So basically we have two choices. Let's say I took a number prime p from this array. So we can start from either p into p, or we can start from the first multiple of p in this range, whatever is bigger. Okay, we will start from whatever is maximum between p into p or l plus p minus 1 divide by p into p. This could seem a lot complex, okay, but this is not actually a lot of complex. It basically means what is the first multiple of number p in this range. Okay, this basically means which is the first number that is a multiple of number p in this range. So for example, let's say we had 2. Okay, let's say we wanted to mark the multiples of number 2 in this range. So why actually are we doing this? In order to save time, since we know that this number is actually very big. So in this case we have taken 50, some other case it could be 10 to the power of 8 or 10 to the power of 10. In that case, running a loop by plus 2 and starting from 4, 6, 8, 10, 20, and in this way going up to 10 to the power of 10 is going to be very costly, and it's going to give you a TLE. So we do a very a small trick. What is the trick? We basically start from the pth multiple of number p, or whatever is the first multiple in that range, whatever is bigger. Okay, so we'll see in some cases this p into p is bigger than the first multiple of number p in that range. Okay, so let's say we had like 2. So 2 was what? 2 into 2 is what? 4. Okay, and L plus P minus 1 is what? 50 minus what? 50 minus P is what? 2. Okay, okay, plus P minus, sorry, 2 minus 1 divided by 2 into 2. Okay, let's try to see what 50 plus 2 is what? 52, 51, 51. 51 by 2 is again 25, and 25 into 2 is what? 50. So this again gives you back 50. Okay, so we can see what is maximum between 4 and 50. We can see it's 50, right? So we can directly start marking our multiples from 50. Instead of going from 4, 6, 8, 10, 12, 14, we can directly skip to 50, because that is our first multiple in the range from 50 to 100. So now what do we do? As we know कि जो multiples होते हैं उनको हम false mark करते हैं, because जो भी multiple है वो simple सी बात है prime नहीं है. Since a number is divisible by number p, okay, since we know that this current number is divisible by some number p, this means that this number cannot be prime. It cannot be prime. It cannot be prime. So what do? We started from 50. We marked 50 as false. So how do we mark this as false? We basically do, since we know that we are actually mapping these values to an array. So like 50 and 100, this marks to 0th index, and this marks to 50th index, right? In this way. So this means we also need to represent how do we get 50. How do we get 50? So let's say let's say this is value, and this is what maximum of p into p, comma what? L plus p minus 1 divided by p into p. Okay, so remember this basically gives you the first multiple of number p in the range L to R. Okay, and this is basically the square of number p. Okay, so like for 2 we got what? We got 50. Okay, so basically how do we mark this as false, that this number is false or not? We basically mark, let's say the name of our array was mark. So we do what? Mark of v minus L. So we see that L was what? L was 50. This is L, this is R. So we mark v minus L as false. So in this case we had what? We had 50. So 50 minus 50 would be what? 0. So basically we can see that we are going back to 0th index. We are mapping to the 0th index, and we mark it as false. So basically this means that 50 is not a prime. Okay. So now let's move forward in a similar way. Okay. Let me take this. Okay. So first of all, we start with 50. Okay, then we'll go in the same fashion. Okay, just in the similar C fashion, that we just update j plus equal to y. So we'll just use the same thing, that from 50 onwards we'll go to 52, then 54, then up to 100. So now a lot of some of you might say that भैया ये तो number range काफी बड़ा है. Right. Remember, the initial constraint that we had, the initial limitation that I said is that R minus L will only be 10 to the power of 6. The difference range, जो आपकी range है, वो हमेशा 10 की power 6 के अंदर अंदर होनी चाहिए, उससे बड़ी नहीं जानी चाहिए. ओके, चाहे नंबर जितने बड़े हो, अगर कल को आपके 10 की पावर 10 भी होते हैं ना, नॉट अ प्रॉब्लम. अगर आपका ये L है तो आपका R 10 की पावर 10 प्लस 10 की पावर 6 होना चाहिए. So इससे क्या हो रहा है? The difference between L and R always remains bounded by 10 power of 6. So that is the point. Okay, अब इस रेंज के ऊपर आइटरेट करना is not going to be a problem. अगर आप इसके ऊपर आइटरेट करोगे, so it's very similar to what we were doing in the original sieve algorithm. Okay, so we'll mark 50, 52, 54 up to 100, all the numbers as what? जो भी 2 के multiples are as as false, that they are not prime. Then we go to 3. The next prime number was 3. Okay, so again we have what? We have to, we will take the maximum of 3 into 3, and what? 50 plus 3 minus 1 divided by 3 into 3, the first multiple of 3. So we have what? 9, and then 50 plus 3 is what? 52. 52 divided by 3 is what? 52 around is what? Let's take a guess. Let's take a similar guess. So 50 by 2 is what? Okay, so we know that this is what? This is around 17, because 17 3 is 51. So 50, 17 into 3 again 51. So we can see that the first multiple of number 3 in the range 50 to 100 is what? 51. So we'll start marking from 51. So we'll mark 51 minus 50 as false. Remember, we are going to mark what? 51 minus 50. Okay. Mark what? Value minus L. Okay. So we'll always mark what? We'll always mark v minus l, whatever the value is, with the lower range, so that it gets mapped to that index range. हमें इसकी मैपिंग भी करानी है उस इंडेक्स रेंज में 0 to 50 की इंडेक्स रेंज में, right? So that's why 51 basically means what? 51 basically means the first index in that array, right? So this will be mark of 1. So mark of 1 basically means 51. This we mark as false. Then we go to what? 51, then 3 is what? 54, then 57, then 60, then 63, and then so onward we'll go up to 99, right? We'll cover up to 99. So all these numbers will be marked as false. Okay, will be marked as false. Now we have covered 2, 3. Now we go to 5. Now we go to 5. Okay. So now for 5, what do we have? Maximum of 5 into 5, comma, what? Comma like, what? It was 50 plus 5 minus 1 by 5 into 5. Okay. So you can directly see that the first multiple of 5 is actually what? 50, right? So we directly know that, if you, even if you do this, this is what? This is 55 minus 1 is what? Around 54. 54 divided by 5 will give you around 10 only, and 10 into 5 will give only 50. This will give you 50. Okay, and this is 25. So again we'll start from 50. We'll again start from 50. So now we basically know that this has been already marked. So 50 basically means 0th index. Then we go to 55. 55 is what? 5th index. Then we go to 60. 60 has already been marked. This is what? This is 10th index. Then we go to 65. This is 15th index, and so on up till 100. So 100 will already be covered by by 2. So that is basically not a problem. That is not of our concern, that we are going to cover something multiple times. As in previous sieve algorithm, we have also seen that the multiples which are bigger, if even if they have already been covered, we still cover them again if they are bigger multiples, right? Like for example, for 6, like not for 6, let's take some like number like 12. So 12 was initially covered by 2. It was again covered by 3. Okay, so we can see that even if the multiple is bigger, then we can cover the multiple times, but that is not going to change the runtime of the algorithm. It's still going to be same, because we are bounded by the difference of the range. Okay, the range difference is still small within that we can efficiently compute these things. Okay, so we'll mark all the multiples of number 5. Okay, then we go to finally the number 7. We finally go to number 7. So what do we do? Again, 7 to 7 is 49, and the first multiple of number 7 is what? 50 plus 6, 56 divided by what? 7, and 7 8 is 56, and I think 56 is actually the first multiple of this thing, right? So as far as I can see, yeah, this is the first multiple, so it will again land back to 56. So instead of 49, we'll start from 56. So 56 is what? Basically 6th index. Then we have what? 62, not 62, 63. 63 will be marked to what? Will mark to 6 plus 7, 13th index. Then we have 63 plus 7 as 70. So 70 would be 20th index. And in this way, we'll again move on to up till 100. So after this is over, what we have done, we have marked all the multiples of the prime numbers. So now remember this is a very important step in our complete algorithm. When we have marked all the multiples of prime numbers, what did we do? We marked all the multiples of prime numbers from 1 up to SQRTR 2, 3, 5, 7. Then whichever number are left between L to R that are unmarked, which have still not been marked, are basically the numbers that are prime in between L to R. Okay, so since this range was very big, so I cannot actually show you. When I'll write the code, I'll just show you which all numbers were prime. So basically, after we are over this marking of multiples, the numbers from L to R which are unmarked, okay, which haven't been marked as false, will be the numbers which are prime in between L to R. Okay, whatever number are prime from L to R will be unmarked. And this is how very elegantly and very beautifully this algorithm works, and find the numbers, prime numbers even in a bigger range. Even when we have bigger values, it still is able to find, mark the prime numbers in that range, given that the difference range is not very big. Okay, it's 10 to the power of 6 around, it is equal to or less than that value. Okay, and the time complexity still remains the same. So first of all, calculating that thing, first of all, since we are going to use what that for finding the prime numbers from 1 up to SQRTR, that you can basically take as what? SQRTR into log of SQRTR, right? That was our first step. Okay, this was our time complexity of first step. Okay, and for the second step, it's again the same. We use what? r minus l plus 1, because we know that we are marking the difference range. So this will be similar. This will be r minus log of r minus l plus 1. So since we know that this value can go up to the power of 6, this value also go up to the power of 6. So we can easily say, we can, without any problem or without any, worry, we can say that this code or this algorithm is going to work fine. It will pass the test cases. It will efficiently calculate the prime numbers in between that range, given that this, this condition is satisfied. Okay. And remember, the value of r cannot go beyond 10 to the power of 12. Okay. This is not recommended. This is not possible. Why? You can see that initially, since we are going to mark the, the prime numbers from sqrt r up to 1 up to sqrt r, that's why, let's say, if you take 10 to the power of 14, you would not be able to make an array of size 10 to the power of 7, right? Or 10 to the power of 8. So that's why we are bounded by this value of r, that r cannot go beyond 10 to the power of 12, because if it goes beyond, we would not be able to calculate the step 1, and that is actually very necessary, very important to this segmented sieve algorithm. So that's why, if the value of r and l are well within 10 to the power of 12, and the difference range is within 10 to the power of 6, you can easily employ segmented sieve for your problem. Okay. So we have discussed the time complexity. We have discussed how this algorithm works. Let's go down to the code part and actually see how this algorithm performs. Okay. Okay, so let's start with the implementation part. So first of all, we'll define some basic things like LL for long, and then hash include bits slash stdc ++ .h. Okay, pardon my speed, using namespace is std. Okay, so this is namespace. Okay, so let me just check if everything is visible. Let me just increase the size. I think this should be visible now. Right, yeah. Okay, this is visible. Let me just make this down. Okay. Okay, so let's start with the segmented sieve algorithm. So first of all, we'll take our two inputs, since these numbers can be very big, so they might not fit in the normal int range. So because of that, we have taken long. So we'll take two inputs, the value of L and R, and we'll take L and R. So now what do we do? Now we do go for step 1. Step 1 is what? Calculate all primes from 1 to sqrt of R, right? So let's define a variable limit as what? As sqrt of R. Okay, and then we'll create our initial vector, that so this step will actually use the same sieve of Eratosthenes algorithm. Okay, so you can actually copy, or whatever you want. So I'll just write it from basic primes of what? Limit +1, just to be on the safe side. And initially we'll mark everything as true, as we did in the initial sieve algorithm. And now what do? We might mark prime of 0 equal to primes of 1 as false, because these two numbers are specifically always not prime. Okay, so now we'll start our step 1. So as we know, I equal to 2, I into I is less than equal to limit and I plus if primes of I, since it is already prime. So what do? LLJ would be equal to what? I into I. J is less than equal to lim and J plus equal to I. Okay, so you can actually go back and refer to the code of sieve of Eratosthenes. So what we are writing here is basically the normal sieve of Eratosthenes code. Okay, because यहाँ पर R हमारा छोटा है, हम sqrt_r ले रहे हैं. Okay, that's why sqrt_r is around 10 to the power of 6. So हम यहाँ पर क्या करेंगे? सबसे पहले सारे प्राइम नंबर्स को एक्सट्रैक्ट कर लेंगे इस रेंज में. Okay, so what do? We mark primes of J as what? As false. Okay, that these numbers are not prime. Okay, so this is done. Marking of primes is done. Okay, so now what do? Step 2. Step 2 was what? Step 2 was extract all prime numbers. Okay, so for this purpose, what we'll do? We'll just create a simple PR array. So PR basically, or let's say prime. Let's name it as prime, or let's say prim. Okay, just to avoid confusion, we'll name it as prim. So now what we'll do? We'll just push all the prime numbers from that we have marked in this array, in this primes array, into this prim array, in this prim vector. All the numbers that are prime. Okay, we'll just push them into this prim array. Okay, so how do we do it? We just iterate over from LLI equal to 2, I less than equal to lim, and I plus if primes of I, then what do? We do prim dot pushback I. Okay, so now we have extracted all the prime numbers from 1 up to sqrt_r. Now we'll go to the main important part of this whole algorithm, that is step 3. Mark the multiples of prime numbers calculated in L to R range. Okay, so for this thing, what we'll do, first of all, we'll need to create the final prime array that will basically, we'll name it as mark. So mark will basically denote the range from L to R. We'll map the range from L to R into this array. So the size of this array would be what? This would be R minus L plus 1. Okay, I'll just write it down. R minus L plus 1, because we are mapping that complete range L to R into this array. That's why the size of this array is R minus L plus 1. And initially what we'll do, as we do, we'll mark every one of them as true. Every number is marked as true. Okay, now we start proceeding. So first of all, we take up auto p from prim array. So what do we do? We not auto, let's like ll. Okay, so what do we do? We extract a prime number that we have calculated from the before step, from the previous step. Okay, this prime array में जितने भी हमारे prime factors आए थे, prime numbers आए थे, अब हम उनके multiples को एक एक करके mark करना शुरू करेंगे. So what do? We take up a prime number from this array, from this vector, and then we mark all the multiples of this number p, prime number p, in the range from L to R. And how do we do it? We create another loop. LLJ is equal to what? As we said, maximum of what? Maximum of p into p, or L plus p minus 1 divided by p into p. So just to avoid confusion, I'll just write a parenthesis. So remember, why are we doing this? This we are doing just to reduce the processing step, because if the number was like we saw in the example that like we had to start from 2, and we start 2 4 6 8 10 12 50 10 12 16. So in order to avoid the useless iterations like 2 4 8 16, because they are way smaller than what we are actually going to work on, because the value of L can be very big in comparison to what the prime factors we had, right? We had prime number as 2, but the L can be 10 power of 8. So starting from 2 and going up to 10 power of 8 can be very very tedious, and it would give it ideally. That's why we directly jump from either p into p, whatever is maximum p into p, or we take the first multiple of number p in the range from L to R. This formula, this thing basically comes from basic number theory, not number theory, or even if you have basic common sense, you can actually derive it on your own. That this basically gives you the first multiple of number p in the range from L to R. Okay, so we get that, and whatever is the maximum, we start from that. Then we just write the same, j is less than equal to R, and j plus equal to what? P. Okay, now since this range is 10 power of 6. Okay, so that's why this loop will easily work. ऐसा सोचने की जरूरत नहीं कि नंबर्स बहुत बड़े हैं तो भैया बहुत लंबी रेंज है. हमने बार बार बोल चुके हैं, बार बार डिस्कस कर चुके हैं that this range can easily work because 10 power of 6 की रेंज है. Okay, so now what do? We mark j minus what? J minus L as false. This is a very important step. What do? We mark the value j minus L as false, not L, because remember L comma R has been mapped to this mark array from 0 to R minus L plus 1. हमने इसको मैप किया 0 से लेके R minus L के बीच में, राइट? तो रिमेंबर कि जो हमारा L है बेसिकली ओरिजिनल L है, that will map to 0th index. L plus 1 will map to first index. L plus 2 will map to L plus basically second index. So that's why we mark of j minus L equal to false. So this is basically equivalent to saying that L plus 2 or whatever j is, let's say j was L plus 1, and if it is if it satisfies this condition, then we basically say that j minus L or L plus 1, let's say j was L plus 1, that L plus 1 is not a prime, right? By marking mark of 1 as false. Okay, after we are over with this marking step, we'll just handle a very edge case, and that is what? That is, let's say if L was 1. If L was 1, so that's why just to make sure that 1 remains false, because let's say in case we start from 1, then it might be possible that we're not going to cover 1. So if the initial value of L, that is the starting range, is 1, so we'll specifically mark 0 as false, that so that we do not incorrectly mark 1 as a prime number, because 1 is not a prime number. So this is basically an edge case handling. Okay, and after these three steps, that first of all we calculate all primes from 1 up to SQRT, then extract all the prime numbers in that range that we have calculated. Then we basically mark the multiples of those prime numbers in the range from L to R. Finally, we are actually ready to print all the prime numbers from L to R. And how do we do it? I equal to 0, I less than equal to what? R minus L. What was the size? Let's say mark dot size I plus plus. And if what? If mark of I is true, then which number is actually prime? Let's say if the ith index is unmarked. Okay, if it is still unmarked basically means that it is still true. Then which number is actually prime? Then actually the number L plus I is prime, right? The number L plus I is prime. So remember this. If the ith index is unmarked, which means it is still true, it basically means that the number L plus I is prime, right? And then we just /n. So now we are over with the implementation. Let's try to run this piece of code. Let's run this segmented sieve. Okay. So I hope everyone is able to understand what I'm trying to implement here. Okay. Then /a.exe. Okay. Now let's try to give the numbers. Let's take 50 and 100 only. 50 and 100. So we can see 53, 59, 61, 67, 71, 73, 79, 83, 89 and 97. These are basically the prime numbers in the range from 50 up to 100. Let's check it again. Let's check it. Let me check. Numbers from 50 to 100 prime. Let's check. So basically we can see, as we what I can see from a Google search result is that the numbers at a prime are 53. Okay, we have 53, we have 59, then we have 61, then we have 67, then we have 71, then we have 73, then we have 79, then we have 83, then we have 89, then we have 97. So we can see this algorithm works perfectly. Okay, let's try out some bigger numbers. Let's say we have like 10 to the power of 8. Okay, this is 4 and then 4 more zeros. I think I'm within the range. Okay, 4 and 4, yeah, 10 to the power of 8. And then the range can be what? 10 to the power of 8 plus 10 to the power of 6. Okay, so 10 to the power of 8, I take, let's say, let's take 100. Okay, this is 4. Okay, so this is basically 10 to the power of 4 range. 10 to the power of 4 numbers. Okay, so we can see that all prime numbers in this range have been marked. Okay, they have been marked. Okay, and you can also use this same algorithm for marking the basic numbers. Let's say आपको 1 से लेके n तक के numbers चाहिए. Okay, this segmented sieve can also work as a normal sieve. Okay, वो कैसे काम करेगा? Let's say आपको बस कुछ नहीं करना है, L को 1 दे दो और जो भी आपको n रखना है, let's say 50 दे दिया आपने. It will work similar as a normal sieve. Okay, so we can see that segmented sieve is actually very flexible. अगर आप L और R को define कर दो तो it works just same as a normal sieve. Okay, but L और R अगर बड़े हैं, so then you can just go ahead and you can try out any values. जैसे हमने दिखाया, you were able to print all of the values, right? So चाहे नंबर कल को 10 power of 12 भी आते हैं, let's take 10 power of 10 लेते हैं. ठीक, कुछ बड़ा नंबर 1 2 3 4 5 6 7 8 9 and then what 7 8 9 then 10. Okay, this is the initial start. Then we have what 1 2 3 4 5 6 and then 7 8 9 and 10. Okay, so I would like to just 0 0. Let's take, if it is correct, 4 4 8 and to 10. Yeah, right, I think this should work fine. Yeah, so we can again see that all the prime numbers in the range have been marked. Okay, these are basically all the prime numbers from 10 to the power of 10 up to 10 to the power of 10 plus 10 to the power of 5. Okay, remember, difference range बहुत important है. So in this way, basically the segmented sieve works. So I'll just go through the code part again. So what do? You basically, it has 3 steps, 3 major steps. First of all, you calculate the prime numbers from 1 up to sqrt of n. Remember, not n, but sqrt of n, right? By using the normal sieve algorithm. Then you extract those prime numbers from the sieve that we have. Okay, and we store them in any array. Let's say prime array or prim array. Then we start marking the multiples of that of the prime numbers that we have extracted in the range from L to R. Okay, हम हर एक प्राइम नंबर जो था हमारा उस रेंज में उसको उठाएंगे और उसके जो मल्टीपल्स थे L से लेके R के बीच के रेंज में उनको मार्क करते जाएंगे and in this way we'll mark them up. And this is the special case that let's say if L was 1, so उसको अलग से हम हैंडल कर लेंगे, स्पेसिफिकली वो मार्क हो जाए कि it is false because 1 is not a prime number. And towards the end, we just print those numbers that if the ith index is prime, this basically means that the number L plus I was prime. And in this way, basically, segmented sieve works. So that was all for today, guys. I hope that you were able to understand that how segmented sieve works, what is the benefit of using segmented sieve, and how even when the numbers are big enough, and for a lot of problems, this would come in handy and very beneficial, very excellent algorithm, right? So अब जाओ इसके बेस पे questions भी बहुत सारे available हैं. You can go ahead and try out questions on Leetcode or Geek for Geeks or on Code Forces or Code Chef or any coding platform that you like. You can go ahead and try out the question on based on segmented sieve. Okay, and if you like the content, if you like the understanding, the go through the concept overview, then you can like, share, subscribe. Do comment if you understood the algorithm, if you understood how segmented sieve works, then do comment understood or whatever you want to like or whatever you want to give a suggestion. Okay, do like, do share this video with your peers and with your other friends. Also, keep on practicing, watch the videos till the end. If you're new to the channel, then do subscribe, hit the bell icon so that you never miss an update. And for this video, we are over. From next video onwards, we'll be covering some other topic. I mean, number theory is still not over. Arrays and mathematics is still, in the process. We have actually a still lot of things in number theory itself that we are going to cover in the further videos, since this topic needs a specific attention. That's why I'm covering these topics specifically in over one video. So this video is complete for now. So we'll meet in the next video with some other topic. Till then, bye bye guys. Keep practicing, keep grinding. Bye bye.